For decades, space telescopes such as the Hubble and the James Webb have dominated the greatest astronomical discoveries. But now, a ground-based observatory has surprised the scientific world. The Vera Rubin Observatory, located atop Cerro Pachón in Chile, has released its first images and revealed a universe more vast, dynamic, and detailed than many had imagined. But first, don't forget to like this video and subscribe to our channel. Designed to observe the sky continuously, Rubin does not operate like a traditional telescope. Its goal is to record constant changes throughout the cosmos, creating a kind of time-lapse movie of the universe. At the center of this revolution is the largest digital camera ever built, capable of capturing an astonishing 3,200,000,000 pixels in a single image. The scale of its observations is extraordinary. Each exposure covers an area of the sky equivalent to dozens of full moons, allowing millions of objects to be recorded simultaneously. In just its first hours of operation, the observatory identified interacting galaxies, star-forming regions, thousands of ancient clusters, and a remarkable number of new asteroids. What makes Rubin unique is its ability to revisit the entire visible sky every few days. This allows it to detect stellar explosions, moving objects, brightness variations, and transient cosmic events in near real time. Rather than producing only static images, it will track the evolution of the universe over the coming years. Scientists believe the project will transform fundamental areas of astronomy, including the study of dark matter, dark energy, and the small bodies of the solar system. And this is only the beginning. The first images already demonstrate that Vera Rubin is not just another telescope. It is a new way of observing the cosmos, capable of revealing phenomena that have remained invisible until now, and that may redefine our understanding of the universe. This is not a telescope built to observe a single object. It was built to observe everything at once. When Rubin captured its first images in June of 2025, astronomers expected something impressive, but they were not prepared for what the observatory would actually deliver. After just over 10 hours of test observations, Rubin produced a mosaic that the scientific community quickly nicknamed the Cosmic Treasure Chest, a breathtaking portrait of 25 square degrees in the southern region of the Virgo cluster, the nearest large galaxy cluster to the Milky Way. This image, composed of 1,185 exposures, contains millions of stars and galaxies. Spiral galaxies slowly stretch their arms across space. Galaxies in the process of merging intertwine like cosmic smoke. Filaments connect distant clusters into structures resembling a gigantic web. In the background, almost invisible without magnification, lies an ocean of faint, reddish galaxies, each potentially hosting billions of planets. And most impressive of all, this visual richness represents only a tiny fraction of what the Vera Rubin Observatory will reveal. These first images account for approximately 0.05% of the data that will be collected over the next decade. By the end of its primary mission, the observatory is expected to catalog roughly 20 billion galaxies, creating the most detailed map of the universe ever produced. The inaugural images already demonstrate extraordinary observational power. Among them is a vast mosaic of the Lagoon Nebula, a gigantic star-forming region located approximately 5,200 light-years from Earth. Unlike traditional images that focus only on the nebula itself, Rubin revealed a much broader cosmic landscape, showing newborn stars, stellar clusters, and structures spread across immense distances within a single capture. Objects such as the Trifid Nebula, Messier 21, Bochum 14, and the globular cluster NGC 6544 appear together in the same image, allowing scientists to observe different stages of stellar evolution simultaneously. This capability is the result of the telescope's enormous field of view, which can capture an area equivalent to dozens of full moons at once. While telescopes such as Hubble provide extremely detailed observations of specific regions, Rubin combines depth and scale at an unprecedented level. For the first time, structures that were once studied in isolation can be observed within a much larger context, revealing connections between the birth, evolution, and death of stars. But Rubin's true purpose extends far beyond producing spectacular images. It was designed to continuously monitor changes in the sky, detect transient phenomena, and record the evolution of the cosmos in real time. And these first images make it clear that the astronomical revolution scientists anticipated has already begun. In just 10 hours, the observatory identified 2,104 new asteroids, including 7 near-Earth asteroids. To put that into perspective, observatories around the world detect, on average, approximately 20,000 asteroids per year. Rubin is expected to discover millions of them within its first years of operation. It may become the most important tool humanity has ever created for detecting and tracking potential impact threats long before they approach our planet. And this is only one of its 4 major missions. Rubin will also seek to understand dark matter and dark energy by mapping how galaxies cluster and move across billions of light years. It will monitor transient events such as supernovae, gamma-ray bursts, and stellar tremors, capturing them in real time thanks to its rapid observation cycles. But the true power of the Vera Rubin Observatory goes far beyond its stunning images. Over the next 10 years, it is expected to identify approximately 100,000 RR Lyrae stars, which astronomers use as cosmic landmarks to map the most distant regions of the Milky Way with unprecedented precision. Behind this mission lies a scale that is almost impossible to imagine. Approximately 500 petabytes of data will be collected during the survey. This represents billions of celestial objects observed repeatedly and trillions of measurements, creating a gigantic time-lapse movie of the universe's evolution. Scientists believe it will take decades to fully analyze everything Rubin records. What makes this achievement even more extraordinary is that it is being accomplished from the surface of Earth. Historically, space telescopes such as Hubble and James Webb were created specifically to escape the distortions caused by Earth's atmosphere. Air turbulence, temperature variations, humidity, and suspended particles normally limit the quality of ground-based observations. Rubin challenges that limitation. Installed on Cerro Pachon in the Atacama Desert, one of the driest, darkest, and most stable regions on Earth, it takes advantage of exceptional atmospheric conditions. By combining this privileged location with a sophisticated 3-mirror optical system, the largest digital camera ever built, and fully automated operations, the observatory produces images whose quality rivals that of many space telescopes. The result is a new generation of astronomical observations. Rather than competing with orbiting observatories, Rubin complements their capabilities, allowing ground-based and space-based telescopes to work together in unraveling the greatest mysteries of the cosmos. And its first images already show that this new era of astronomy has begun. One of the most impressive achievements of the Rubin project is not the telescope itself, but the invisible digital infrastructure required to interpret everything it captures. Rubin is expected to collect approximately 20 terabytes of data every night, a volume so enormous that traditional astronomical networks would collapse under the load. To overcome this challenge, engineers built a dedicated 100 gigabit per second connection that transmits data directly from Chile to a processing center in the United States. From there, the information enters a real-time processing pipeline that calibrates images, aligns exposures, corrects distortions, identifies moving objects, classifies transient events, and integrates new data into an ever-expanding celestial map. All of this happens before scientists even begin their analyses. What Rubin is creating is not a collection of images, but a dynamic digital universe that updates every 3 days. But the most revolutionary feature of the Vera Rubin Observatory is not just the quality of its images. It is the way it observes the universe. Instead of producing static maps of the sky, Rubin creates a living, continuous record of the changes taking place throughout the cosmos. If a supernova suddenly explodes, it will detect it almost immediately. If an interstellar object crosses the solar system, it will be able to track it. If a star begins varying its brightness in an unusual way, every detail will be recorded. Rubin was designed for the era of big data, transforming the night sky into a gigantic database that is constantly being updated. Every 3 nights, the observatory completes a survey of the entire visible sky of the southern hemisphere. This makes it possible to follow transient phenomena with a speed never before achieved. Supernovae, gamma-ray bursts, tidal disruption events, variable stars, and shock waves moving through nebulae can be observed in near real time. This capability completely changes the way astronomy is conducted. In the past, many of these events were discovered too late or simply went unnoticed. Now, Rubin functions as a true cosmic alert system, identifying changes and sending instant notifications to observatories and scientists around the world. Instead of viewing the universe as a collection of static images, astronomers will begin observing it as a dynamic environment in constant transformation. Every explosion, collision, or stellar birth will become part of an enormous temporal record of the cosmos. In addition, Rubin will use ancient RR Lyrae stars to create the most detailed map ever produced of the outer regions of the Milky Way. By combining billions of observed objects over an entire decade, the observatory promises to reveal previously unseen phenomena and answer fundamental questions about the evolution of the universe. These stars vary in brightness in predictable cycles, allowing astronomers to calculate their distances with extraordinary precision. Rubin has already identified 46 RR Lyrae stars in its test images alone, and scientists expect that number to grow to 100,000 throughout the full survey. These stars are often located far from the Milky Way's core, drifting through the outer regions of the galactic halo, or even extending into intergalactic space. Tracking them creates a skeletal map of our galaxy, revealing faint tidal streams left behind by past collisions, hidden dwarf galaxies, and the true 3-dimensional shape of the Milky Way's outermost regions. For decades, astronomers struggled to map these distant areas because the stars were too faint and too widely dispersed. But Rubin's enormous field of view, deep imaging capabilities, and repeated surveys turned the impossible into routine. The Vera Rubin Observatory was not designed merely to photograph the universe, but to map it on an unprecedented scale. Throughout its 10-year mission, it will serve as a true cosmic cartographer, recording the structure of the Milky Way and revealing entire chapters of our galaxy's history hidden within the stars themselves. At the center of this revolution is the largest astronomical camera ever built. With an astonishing 3,200,000,000 pixels, nearly 10 feet in length, and 189 high-precision sensors, it is capable of capturing wavelengths ranging from ultraviolet to near-infrared. Every observation gathers an enormous amount of information invisible to the human eye, including chemical signatures, temperatures, motions, and gravitational distortions. Rubin's optical system is equally extraordinary. Its massive fused silica lenses and 3-mirror design were developed to maintain the same sharpness across the entire field of view. allowing stars located at the edges of an image to appear just as detailed as those at the center. But what truly sets Rubin apart from observatories such as Hubble is its scale. While Hubble produces extraordinarily detailed images of small regions of the sky, Rubin captures areas equivalent to dozens of full moons in a single exposure. This makes it possible to observe not only individual objects, but also the connections between them. Rather than showing only a single galaxy or isolated nebula, Rubin reveals the surrounding environment, the cosmic filaments connecting gigantic structures, and the complete large-scale architecture of the universe. If Hubble offers a detailed portrait through a single window into the cosmos, Rubin reveals the entire landscape surrounding it. More than a telescope, Rubin represents a new way of seeing the universe and understanding our place within it. In that sense, the two observatories complement each other. One is a microscope, the other is a panoramic drone flying above the cosmic landscape. And Rubin's first images prove that the universe looks very different when we finally step back far enough to see the bigger picture. Skyviewer.app is not merely an educational tool. It is an invitation for anyone, anywhere, to explore data that was once accessible only to professional astronomers equipped with high-performance computing systems. Because Rubin's images are enormous, some built from more than 1,000 exposures, navigating through them is like moving across a living map of the universe. A user can dive from vast cosmic landscapes into clusters, then down to individual stars, and eventually reach galaxies that appear as faint points, visible only at full resolution. The platform marks the beginning of something revolutionary, a world in which citizen scientists and enthusiasts participate directly in discoveries. Hidden supernovae, rare stellar pulsations, faint comets, and even interstellar visitors may first be spotted by someone casually exploring Rubin's mosaics. Astronomy is becoming democratized thanks to Rubin's openness, and with half a petabyte of data arriving every year, the scientific community will need every set of eyes it can get. Astronomers estimate that an interstellar object passes through our solar system every year, but until recently, we lacked the capability to detect most of them. Objects such as Oumuamua and 2I Borisov were discovered almost by chance, slipping through our instruments with only days or weeks of visibility. Rubin changes that. Its wide field of view and rapid 3-day survey cycle make it possible to identify faint, fast-moving objects long before they approach the sun, precisely during the period when they are easiest to study. During its first test run, Rubin identified more than 2,000 new asteroids, including several near-Earth objects, demonstrating that it is already capable of detecting unusual trajectories. For interstellar science, this is transformative. Rubin may detect dozens of interstellar visitors throughout its decade-long survey, giving scientists the opportunity to analyze their composition, structure, and motion in real time. These objects are samples from other solar systems, materials formed around alien stars, carrying chemical histories unlike anything we have encountered before. As a result, Rubin may become humanity's first reliable gateway for studying the raw debris of distant worlds. And with enough detections, researchers may even begin answering questions that Oumuamua raised but never resolved, including whether some of these visitors are entirely natural or not. In the end, what the Vera Rubin Observatory revealed in its first images is not simply a new chapter in astronomy. It is the beginning of an entirely new language for understanding the universe. For decades, our view of the cosmos was shaped by narrow windows, tiny fields of view, isolated images, and specific regions of space, studied one at a time. But Rubin completely breaks that paradigm. Its first images already show us that the sky is not a silent dome sprinkled with stars. It is a dynamic tapestry in constant motion, overflowing with structure, evolution, and phenomena that we have barely begun to classify. A single mosaic captures millions of galaxies at once. The first observations from the Vera Rubin Observatory have already made it clear that we are entering a new era of astronomy. In just 10 hours of observation, the telescope was able to identify thousands of previously unknown asteroids and reveal cosmic structures on a scale that would previously have required years of work and the combined efforts of countless observatories. A single image can show far more than an isolated nebula or galaxy. It reveals the entire surrounding environment: clouds of gas, stellar clusters, cosmic filaments, and entire populations of stars connected within the same landscape. For the first time, astronomers can observe the universe not as a collection of separate objects, but as a living, interconnected system. Rubin was designed to create a continuous record of the sky. Every 3 days, it will update its gigantic cosmic map, recording stellar explosions, supernovae, gamma-ray bursts, interstellar objects, and transient phenomena that previously went unnoticed. By the end of its mission, it will have produced approximately 500 petabytes of data, creating the largest astronomical memory ever built by humanity. Its observations are also helping map the deep structure of the Milky Way through RR Lyrae stars, while accelerating the discovery of new asteroids and objects arriving from beyond the solar system. More than a telescope, Rubin represents a complete shift in perspective. The era of astronomy based on static images is coming to an end. In its place emerges a dynamic astronomy capable of following the universe in real time. The discoveries ahead may transform our understanding of galaxies, dark matter, stellar evolution, and even humanity's place in the cosmos. And this is only the beginning of the journey.